All right, let's now get in the real fun of actually modeling a real-life context with one of these sinusoidal functions. In Seattle, Washington, our example says the longest day of the year is June 21st, and it has 16 hours of sunlight. The shortest day of the year is December 21st, and it has 8.5 hours of sunlight. The hours of sunlight can be modeled with a sinusoidal function. That's a big deal, either sine or cosine, with a period of 365 days. Makes sense, one full year. What we're being asked to do is to estimate the number of days that have more than 14 hours of sunlight. Importantly, for examples like this, we can't directly go and attack the question in hand, estimating the number of days. What we're first going to do is to build a model of this information, a sine or cosine function with some transformations so we can model exactly this information. Then once we have our model, we'll go attack this question of the 14 hours of sunlight. So I'm looking for a function that models the hours of sunlight in per day per year. And again, I'm giving these days per year and told you I have a period of 365. So what I'm going to have is, this is on the x-axis, it's the day of the year. And I'm going to have number of hours of sunlight. I also know that I'm going to have a period of 365. And let's see what information I have right here. So first of all, I know that on day 172, there are 16 hours of sunlight. And so again, it's just very rough. It's about halfway through the year. I'll call that a 172. On day 172, I'm up to, let's call that 16 right here. So that point is 172, 16. Again, inputting the day, outputting the number of hours. So that's 16 right there. I'm also told that on day 355, I have 8.5 hours of sunlight. And so 355 is somewhere right here. And that's about half. So how about I call that 8? I'll call that 9, and so my point is somewhere in between there. Again, doesn't really matter, but I want to have some good information on here. So that's 355, 8.5 is that point. And really that's all I need to sketch to work on this information, but it feels incomplete if I don't kind of draw some kind of wave curve here. So we'll draw in a curve, something that looks like that. The drawing here isn't going to really help me in this aspect decide whether sine or cosine. Again, it's going to be my determination of whether I'm working with an equilibrium start point or a max and min start point, but just gives me some feel right here. So let's now attack these different parts. The first thing I'm going to do is find the amplitude. I can find the amplitude of this by taking the difference between the max and the min values and dividing by 2. So first things first, I have my amplitude equals 16 minus 8.5 divided by 2. And I got 3.75 from that work right there. Again, that's going to help me with my A value. I can find this equilibrium point. So there's an equilibrium somewhere halfway in between these two values. And that's really easy. It's almost exactly the same work I just did, except for it's 16 plus 8.5 divided by 2, which would be the average of those two. And I got 12.25. So again, for my graphical information, the 3.75 right there is this gap or that distance right there between the equilibrium and the max, or from the equilibrium to the min value. This value of 12.25 is this y value right here, which is this equilibrium or average value between the max and the min. Last up is finding the b value. I know my period right here is 365 days. I've been told that. And we previously just talked about that the b value in these transformed functions is 2 pi divided by the period, which is 365. When first working with these kind of models, it can seem kind of daunting, but I want to emphasize these three moves right here are almost always the same. you can be given a little bit of different information. Like here we were given the max and min values. We had to determine those are the max and min values from the information that we got. That helped us find the amplitude and the equilibrium right away. Again, these formulas are almost identical. One is subtracting the max and min, dividing by 2. That's giving you this gap of this distance here. When we add them and divide by 2, it gives you the average between the max and min, which clearly should be that equilibrium or the average value of this function. And then we have just this easy formula for finding the b value for taking our normal sine or cosine curve and making sure it has the period that we're looking for. And now we need to make our big decision. Are we going to use sine or cosine to model this situation? We've done most of the work, and all of that work translates whether we use sine or cosine. The choice now is to choose one of them and the correct shift so that this accurately models the representation that we have right here. And again, this is dependent on what kind of information you have. We want this to be accurate, so we want to, as accurately as possible, model this situation. The information that we've been given in this context right here is about max and min values. What I'm going to decide to do is to use cosine because our accurate information are of a max and min values, and I'm going to shift it based on the maximum. So I want to move this function to the right 172. So what I'm going to choose cosine here, and I'm going to plug in a 172 in for C. So here we have a transformed cosine function that models the situation that we were given. Let's now look at a graphical representation of this generated on the computer so it's a little bit more pretty than what I could draw right here. We have this graph. This looks basically what we'd expect. Let's restrict this to one period, so 0 to 365. We can identify these max and min points, and actually it's exactly correct on that point of 172,16. It's a little bit off on that day 355. The reasoning for that, why it's accurate on the 172, because we literally shifted the cosine function so it'd be perfect at 172. The modeling feels good because we're almost exact on that minimum value too. We have this equilibrium that goes right through at 12.25. We don't need to measure it, but we know that the amplitude of that is 3.75. It's the difference between that equilibrium and that max and the min values right there. This goes through one full period on 365 because of this adjustment. And again, just to recap, what we did was chose cosine and this transformation of shifting cosine 172 to the right so that it reached that maximum value of 16 at day 172. Now we have to do the work of finding how many days have more than 14 hours of sunlight. So two different ways of attacking this depending on how we're required to attack this. First of all, if we have the graphical representation here and we throw in the line y equals 14, what we can see is that part of the curve right over that line, those represent the days that have more sunlight than 14 hours or 14 hours or greater. What we want to do is we want to solve this equation when this equals 14. We could answer this with some kind of inequality, but that just gets really messy with trig functions. But what I want to do is solve when is the number of hours of sunlight exactly 14. I know that it happens at two different times. So what I need to do now is solve this equation right here. Importantly, when I solve this equation, I want to really emphasize, and this will be important to remember throughout solving these kinds of equations. When I solve this, and I solve it just for the first period, we don't care about these infinite solutions, I'm going to get two answers from this that will give me both of those days. Those two answers come from when I use the cosine inverse. And this reminds us we had these simpler equations not too long ago, but I'm going to work through all of these steps. Again, I'm going to solve this equation. The x values I get when I solve this will tell me which days, there'll be two of them, which days have exactly 14 hours of sunlight. So in order to solve this equation, what I'm first going to do is subtract 12.25 from both sides. Just so you have an idea, what I'm going to do is I want to isolate this cosine part so I can bring in the cosine inverse. When I subtract 12.25, what I get over here is 1.75 equals 3.75 cosine of all of this jazz. x minus 172. And then I'm going to divide both sides by 3.75. Just show all of that here real fast. So 3.75 divided by 3.75. And when I divide by 3.75, what I get over here is 0.4667. And that's going to equal the cosine of 2 pi over 365 x minus 172. Now that I've isolated the cosine, I can apply the cosine inverse to both sides of this equation, and it's really important what I do in my next step to get my two solutions. So, first of all, I am going to apply the cosine inverse to both sides of this function, or this equation, excuse me. The reason that I apply the cosine inverse is because it cancels out with the cosine right here. So what I'm going to get in my calculator, I'm going to type in the cosine inverse of 0.4667, and I'm going to set that equal to this stuff that was inside the cosine. Because again, the cosine inverse, the whole purpose of the cosine inverse is to cancel out the cosine here. Though when I plug cosine inverse into my calculator and do this work, I'm going to get one solution. But I'm going to use the fact that cosine is an even function, and I'm going to create two new equations. One with the positive version of the output of this inverse function, and one with the negative value of this cosine inverse. So in doing that in my calculator, what I got, the cosine inverse of this value right here is 1.085. And again, what that's going to equal is this stuff that was inside the cosine function. Part of you might be thinking throughout this, why didn't I distribute this 2 pi over 365? Because you could distribute it through these parentheses. But just to be honest, the reason I didn't do that is here's the exact form. If I multiplied it out, I'd probably be inclined to get a decimal approximation. And I'm trying not to use a decimal approximations where I don't need to until the very end. But importantly to say here, this is what I get from taking the cosine inverse of both sides. But I know that actually on the first period, there's two solutions. The second solution comes from the negative of this cosine inverse value. And again, this is a little bit different from what we've seen before, but it's exactly the same treatment. In the example that I'd done previously, solving a cosine equation, I had positive 2 pi over 3 and then negative 2 pi over 3. This is not 2 pi over 3, but this is the output value of that cosine inverse. And these are those negative and positive values. They're both being set equal to what was inside of that cosine function. Now doing the work here, I'm going to multiply both sides of these functions or these equations here by 365 over 2 pi. That will cancel out with that. So 365 over 2 pi. Well, now I'm going to need to use a decimal approximation here because I got a fraction times a decimal. I'll do the same thing down here. In fact, this work will be exactly the same. The only difference here is I'm going to get a negative version of what I have right there. So multiplying by 365 over 2 pi to that. Let's use our calculator and figure out that value. So in multiplying that out, what I got is 63.03 equals x minus 172. Down here, I got negative 63.03 equals x minus 172. And that's really all of the tough work. All I need to do now is add 172 to both these equations. When I add 172 to both sides of this, what I get is 235.03 equals x. That's my first solution right there. And when I add 172 into this, what I get is 108.97. So I have successfully solved the equation for the days that have 14 hours of sunlight. Just to recap that real fast, because this process is really important. I first subtracted out this 12.25, so just subtracted that away, got rid of this a coefficient in front of the cosine by dividing by 3.75. Then came the big step of applying the cosine inverse. Again, the cosine inverse as a function always outputs just one value. That was the whole idea of restricting the domain of cosine, making a one-to-one function. I have this 1.085, but I also know that the cosine of the opposite of this value right here is also equal to this value right here. So I get the 1.085, but I'm also going to create a second equation that's negative 1.085. Importantly, that step, and I like this in this combination of cosine, along with when you're solving quadratic functions or using the square root. You know, when you take the square root of an equation like x squared equals 16, you get this plus or minus. It's actually exactly the same thing with cosine. Totally different reasoning, but exactly the same concept. Of when I apply the cosine inverse, if I want the two solutions that I get on the first period, I need to do the positive and negative value of what I get when I plug in that cosine inverse. I solved both of these by first dividing out this 2 pi over 365. And I got that x equals 235 and x equals 208. The big question I want to answer is how many days of sunlight? Well, it's the number of days between here. So at day, let's say 109, let's just round that to, at day 109, I have 14 hours of sunlight. At day 235, I have 14 hours of sunlight. So if we take day 235, and we subtract day 109, again, we're estimating this gap right here, we get 126 days with 14 or more hours of sunlight.